Good evening. My name is Jeff Thorson, and I'm the Associate Director for TISED, the Trottier Institute for Sustainability in Engineering and Design. Along with Professor Sebastian Gauchal, TISED Director, I'd like to welcome everyone watching to our 5th annual Sedtalks event. I'm pleased to announce that this year, Sedtalks is sponsored by WSP, one of the world's leading professional services firms. In a few minutes, we'll have a chance to hear from Mr. Eric Peisel, an Executive VP of WSP Canada, about WSP's commitment to sustainability and their decision to support Sedtalks and our students. For those who don't know much about the Sedtalks training program, the initiative was created in order to highlight the excellent research that's being carried out by graduate students across McGill's Faculty of Engineering on topics important to transitioning our society towards a sustainable future. The training starts off in the fall with a call to graduate students across the faculty who are performing research in any of the relevant areas towards sustainability. These students then have the opportunity to participate in a series of communication skills building workshops offered in collaboration with McGill's skill sets. This year, we had a special focus on presenting virtually because of this ongoing pandemic that we're in. At the conclusion of these workshops in the winter, December, we hold an event set across 180 seconds, or in other words, your sustainability research presented in 180 seconds. Each of the students involved in the training program have the opportunity to present their work in a 3-minute talk. The committee then selects the 3 students, or ChangeMakers, to continue in the winter training. In the winter semester, the ChangeMakers receive personalized training and coaching on how to communicate their research effectively and prepare engaging presentations. I hope you'll agree with me that their efforts have paid off. At this point, I'd like to welcome the Dean of the Faculty of Engineering, Jim Nicell, to say a few words of welcome on behalf of the faculty and McGill.
Thank you, Jeff. On behalf of the Faculty of Engineering, welcome to our annual Sedtalks event, which is a forum for highlighting innovative sustainability research taking place in our faculty. We know that a transition of our society towards sustainability is essential to long-term prosperity, quality of life, and the future of our planet. And we recognize the incredibly important role that universities must play in this. Universities are the places where the next generation of professionals learn to make sustainability a key part of their life's work. Moreover, universities are the places that have the diversity of peoples and disciplines that equip us with the unique capacity to take on global challenges. I hope I don't have to convince you that McGill is committed to sustainability. As McGill enters its 3rd century, we have made concrete commitments to sustainability through our operations, our research, and our teaching. Similarly, the Faculty of Engineering has made sustainability a core pillar in its educational and research programs. For instance, we've integrated the concepts of sustainability in our engineering, architecture, and urban planning programs. We've established the Trottier Institute for Sustainability in Engineering and Design that draws its faculty and student members from across the faculty and includes many external partners. Moreover, we have played a central role in a cross-cutting interdisciplinary research initiative in the university called the McGill Sustainability Systems Initiative. And importantly, we are a major partner in the New Vic project that will revitalize the Montreal site adjacent to our downtown campus and dedicate it to advancements in sustainability and public policy. When it comes to education and research in sustainability, a key part of what we must do must be to focus not only on conducting the research and generating new knowledge, but to engage with our community. As such, the Sedtalks program aims to highlight the impactful research being done in our faculty, while also helping our graduate students develop public speaking skills and providing a means for outreach to the broader public. Today, we have the opportunity to hear from several of our graduate students, a diverse group covering diverse topics, from improving the design of food storage containers, to addressing antibiotic resistance hotspots, to effectively integrating renewable energy into our existing grid system. Their work is not only a credit to the students and staff involved in TISED, but a credit to all of you who are involved in our activities. That is, an essential part of our work is not only to inform, but to be informed by perspectives from community members and partners who shape our work for the better. Given this, I want to take this opportunity to thank our industry partners who are with us, and in particular, to thank our industry sponsor, WSP Canada, who made this event possible. Sustainability is not simply an academic pursuit. It requires action on the ground, which is why I look forward to hearing about WSP's sustainability strategy and the important difference they make through their work. Thanks to all of you for being part of this conversation. I hope you enjoy the evening's program.
Thank you very much, Jim. I'd now like to invite Mr. Eric Pacelle, Executive VP, Advisory and Innovation at WSP Canada, and a McGill alumnus, to say a few words.
Thank you very much. Good evening, everyone. As introduced, I'm Eric Pacelle and a proud McGill alum, having graduated from the School of Urban Planning. I work for WSP, who is sponsoring this event, and we're a proudly based, Montreal-based firm that's a global company with over 50,000 staff, including 8,000 here in Canada, with 100 offices spread throughout the country. I'd like to thank the Trottier Institute for the opportunity to speak with you tonight. McGill is a strategic partner for WSP, and we appreciate all the collaborations we have been able to create to help students with the opportunity to succeed in their chosen industry after their education is complete. When I was asked to speak tonight, I was told to talk about why WSP would sponsor an event like Sedtalks. I promised to answer that question later in my remarks, but first I want to talk about the world as we see it and how each of you is poised to be leaders we need in our industry. Currently, I think everyone has been seeing the devastating impacts of climate change. We don't have to look any further than what's just happening to my colleagues in Australia. I was just I'm on a call with them a couple of days ago, and I'll be actually having a call with them later this evening. And last year this time there was massive forest fires and bush fires threatening their cities. Today it's flooding that's out there, and we're seeing that climate change is coming on. Our coastlines are eroding, polar ice is thawing. And this has reached a critical point. At WSP, we're working very hard actually with governments throughout the world, including here in Canada, to really develop, infrastructure, buildings, and ensuring that we design sustainably and resiliency. And also really seeing how do we meet our net zero goals that all the countries are starting to come into. It's a journey that we're beginning on, and we're really excited to be accompanying so many of our clients throughout this. But it is an important one that we all have to go forward. This brings me kind of the opportunities ahead. We're really facing unique challenges that are once in our history so far, and it'll have multi-generational impacts. And to do so, it's not going to be solved in 5-10 years. It's going to take time. So for us, all of the new graduates that are coming through these programs are so key and so important, because we're starting some work now, but for us, it's so important to be able to kind of take the future generations and bring them along. We're doing a number of marquee projects. I'd like to bring one out in particular, which is the rehabilitation of the center block at the Canadian Parliament. And, that project is we're taking a historic building and we're actually rehabilitating it for the next 100 years. We're making sure that it's resistance to climate change, to earthquakes, and ensure that it can be enjoyed by millions of Canadians for years to come. At WSP, we talk about the need to be future ready. Being future ready really means being agile, empowered, and resilient, and really is all about sustainability. And we're working on building an empowered workforce that has the tools to really meet these challenges head on. For us, really, all of you are the future of our industry. And for us, it's so vital to work with places like McGill and partner with them to ensure that we're able to work to get the best graduates to really allow us to kind of be coming in. And this makes me reflect on my time at McGill University. As I said, I actually really thoroughly enjoyed my time at the School of Urban Planning. And it's amazing to see how much things have changed. Obviously, as planners, we've always been very kind of sustainably focused. But I remember when I did my thesis over 20 years ago on rapid transit in the Montreal region, there wasn't that many people that were pushing as much for transit. Today, on the other hand, the vast majority of the planning we do in transportation is all around rapid transit, around sustainable transit methods, active transportation. So it's amazing to see how in a relatively short amount of time, only a couple of decades, that we've transformed the way we look at our cities so differently. The car was king 20 years ago. And today, as you can attest in many of the great cities, including Montreal, how much space we're actually taking away from the automobile and we're giving back to its citizens. All of this is really a key piece of what we're seeing in sustainability. And, I would challenge all of you that, through your careers, you're going to see bold changes. And a lot of it is going to be tied to how do we make the future a better place. And I really, really encourage all of you to really push and drive for these things, because we're going to need bold thinking and bold ideas to be able to move forward. Your generation is going to inherit a lot of the things that we'll have started, but we will not have been able to finish. And as engineers, you really have the power to help transform our communities. And same thing as planners as well. I've always found it amazingly fun to see how I've actually been able to change the communities we live in, make them healthier, smarter, and drive those things forward. And the reason we partnered with McGill for these CEDTalks is really, the original question is, my answer is, how could we afford not to? If we don't invest in the next generation of our workforce and provide them with the tools to create a strong, safe, healthy, and resilient infrastructure, we'll fail to create the communities that everyone will succeed in. And we cannot afford to fail. And so that is the reason that here at WSP we're sponsoring these CEDTalks and are so excited to be working with McGill University and with all of you, the next generation, to help develop a better world. And that's the great thing that we at WSP get to do every day, is transform our world bit by bit, and from community by community throughout Quebec, throughout Canada, and throughout the world. Thank you very much.
Thanks very much, Eric. I think it's really wonderful to think about how we can work together to try to make that better world for the future generations, and to instill that into our students at the university and engage them in this process of looking towards a better and more sustainable future for society. So at this point, just a couple of words about the format of tonight's event. We have 3 speakers, 3 change makers. Each are going to present for around 15 to 20 minutes. So that we don't disrupt the flow of the evening, we're going to have a live Q&A session of all of the change makers after the 3rd speaker presents. So in the meantime, we invite you to submit your questions throughout the talks via Twitter using the hashtag Sedtalks2021, or by email at tyzed@mcgill.ca. And now, without further ado, let me introduce our first change maker, Breno Mumic Sequeira, who is a second-year Masters of Engineering candidate student in the Department of Chemical Engineering, studying under the supervision of Professor Anne-Marie Kietzig. Tonight, Breno will tell us how we can redesign the surfaces of plastic food storage containers, which can lead to less food waste and increase the longevity of these containers for more sustainability. Breno.
It is nothing new to anyone that we have been facing a serious problem with plastic pollution for years. The world currently produces 381 million tons of plastics in a year, but only 9% of this amount is recycled. 12% is incinerated, and 79% end up in landfills, which corresponds to 300 million tons of plastics per year. And this amount of plastics in landfills contributes immensely to global warming. And why are there so many plastics that don't get recycled? They were actually on their way to get recycled, but they got rejected in the recycling plants because they have food waste in it. On average, about 25% of the plastics is too contaminated to go anywhere but the landfill. And those who care most about recycling wash out these containers before throwing them out, like what I am doing in this video with the ketchup bottle. But you can see that this is not the best solution for this problem. Since only to wash this ketchup bottle, I spend around 3 liters of water, soap, and 2 minutes of my time. And we cannot count that everybody will do that for all food plastic containers. In fact, most people simply throw out these plastic containers with leftovers in the trash can. But now imagine, what if we have bottles that clean themselves? Well, there are multiple surfaces in nature that have the self-cleaning and water repellency features, like the shark skin, for example. And as an anecdote, scientists have tried to mimic it to produce swimsuits to reduce drag for the Olympics. But it didn't go well as planned, because the skin is attached to a flexible body, and human bodies are far less flexible than sharks. And another example in nature is the mosquito eye. Mosquitoes don't have windshield wipers to remove water and dirt in their eyes. So the rough surfaces of their eyes is what keep them dry and clean. And there are also insect wings and the lotus leaf. And all of these surfaces and many others do not have any kind of coating to have this water repellency feature. They are actually rough surfaces with the combination of micro and nanostructures, as you can see in the magnified images at the bottom. Here you can see how a lotus leaf is repelling water. Check now the microscope images of its surface. It presents both micro and nanostructures, and that's why the lotus leaf has the self-cleaning and water repellency effects. And the lotus leaf is actually one of the best surfaces in nature with these properties. Pretty cool, isn't it? Now imagine if food plastic containers could have these surfaces like the lotus leaf. And that's exactly what my research aims to do. Get inspiration from nature to make food plastic containers non-stick, or more technically, super hydrophobic, through the creation of micro and nanostructures inside of these containers. And that way, you can get the most out of the food that you bought, and not worry about washing any ketchup bottles anymore, since they will be recycled at the end. That's amazing, right? So now let's understand more about the science behind all of this and how I am replicating these structures inside of food plastic containers. First, let's describe hydrophobicity. The word hydrophobic means fear or hatred of water. In material science, it refers to a surface that repels water. But there are different degrees of hydrophobicity. Starting from a hydrophilic material. As you can see in the image, the water is totally spread out on the surface, adhering to it. In a hydrophobic material, you can now see that the water droplets sit on the surface a little more, which is what happens after you wash your car, for example. And at last, we have a super hydrophobic surface, in which the water droplets are mostly rounded, and they can easily roll off the surface, which is the case of a lotus leaf. And this is what I want to do with the food plastic containers. And we can measure how strongly a material repels water or how hydrophobic it is by placing a droplet of water on the surface and measuring the angle between the droplet and the surface. And that is called a contact angle measurement. And to be considered super hydrophobic, the surface needs to satisfy two conditions. First, it needs to present a contact angle equal or higher than 150 degrees. And second, the water droplets must easily roll off the surface with the lowest contact area between the water and the surface. And that brings us to the second variable, the contact area. And as I said before, the main factor to create super hydrophobic surfaces is the combination of micro and nanometric structures, which is also called hierarchical structures. But why do we need this combination? What about only microstructures? Or only nanostructures? Well, let's understand why the hierarchical structures is the desired output. Starting from a flat surface, which is the same as we have in plastic bottles that we buy nowadays. The water droplets is spread out on the surface. And also, the contact area between the water droplet and the surface is the largest, as you can see on the red line. And that's why the droplet gets stuck onto the material. And now if you take a close look into the shape of the water droplets for the case of only microstructures, only nanostructures, and hierarchical structures, they are actually the same, meaning that their contact angle values are the same. What's the difference then? What changes is the contact area. In the case of only microstructures, the contact area between the water droplet and the surfaces decreases when compared to a flat surface. But the water droplets still get stuck onto the surface. In the case of only nanostructures, The contact area is even smaller than only microstructures, improving the ability of water to be removed from the material. But it's not the ideal scenario yet. For the hierarchical structures, the contact area is the lowest possible. And as a consequence, the water droplets easily roll off the surface, characterizing a super hydrophobic material. Check again the lotus leaf example. The water moves around effortlessly, also carrying dirt particles. Isn't that beautiful? And now you need to understand how food plastic containers are fabricated in the industry. They're actually fabricated by injection molding. This process basically uses plastic granulates that are filled into the machine, melted, and pressurized against a metal mold. And in the end, the plastic will replicate the inverse of this metal mold. And what I am doing in my research is creating the hierarchical structures in a metal mold, as you can see in the image in a rough way, testing different set of geometries, formats, and sizes for these geometries. And after injection molding, the plastics will have a mirror version of this mold hierarchical structures. And in the end, I hope that the plastic containers will be super hydrophobic. But one of the main challenges in this process is the replication of the nanostructures on top of the microstructures. In my project, I am using an ultra-fast laser to create these hierarchical structures in a stainless steel mold. In simple terms, the beam produced by the laser precisely blows out my metal mold, as you can see in this image, to create the structures that I programmed. And the purple light is the spot where the beam is removing material. Ultra-fast laser micromachining can effectively create surface patterns on the micro and nanometer scale by using algorithms through Python software. And in order to figure out which sizes for each geometry and their formats will provide the best outcome in terms of superhydrophobicity, I have to do computational thermodynamic optimization. And these are magnified images of my square patches. In my experiments, I am lasing two different formats, pillars and holes, for each geometry that will be tested. Pillars are structures that the laser beam ablates in their contour. And holes, the beam ablates inside of the desired geometries. And 5 different geometries will be tested in the following arrangements: squares, rhombuses, hexagons, cylinders, and triangles. And as I said before, for each of these geometries, both pillars and holes formats will be tested. And so far, most of the Python codes to create these structures in the laser in both formats are ready to use. But only square and hexagons geometries have been tested so far. The computational thermodynamic optimization considers 2 main factors. First, the final polymer must have a contact angle of at least 150 degrees. And second, the droplet of water should be maintained on top of the hierarchical structures, so that the water can roll off easily from the surface. In other words, we are decreasing the friction by reducing the contact area between the water droplets and the surface. Otherwise, if the water gets inside of the structures, like in the first image, even having a very high contact angle value, the water droplets will get stuck into the surface. And that's undesirable. So if you remember, these 2 factors are the ones that will guarantee that my final polymer will be super hydrophobic. And then, after inputting them for optimization, the software provides me the structure sizes for each geometry and their formats that will have the highest degree of hydrophobicity. And after this step is finished, the optimized geometries for each geometry are lased on my metal mold and molded in the laboratory at McGill before being tested in an injection molding at the industrial site. And this is where I'm currently at with my project. And these are actual heat map images from a couple of my results on my mold and their polymer replicas after molding in the lab. In the top part, you can see that square pillars were laced in the metal mold, and as a replica in the plastic, we have square holes. The bottom images are the inverse. The square holes laced in the mold and square pillars molded in the polymer. And so far, the square holes replicas presented the best hierarchical structures replicas. And in the zoomed image from the top of a square pillar, you can see that it is flat, without the nanostructures needed to create the hierarchical structures. However, on top of square holes, you can see the replicated nanostructures on top of the microstructures as desired. And the failure in replicating the nanostructure on top of pillars is due to the fact that the polymer cannot penetrate the holes completely in the mold because the air gets trapped. And that's why no nanostructures can be seen on top of pillars in the plastic. And then, after successful replication of hierarchical structures on the polymer for square holes, the plastic sample will be tested in the goniometer, which is an equipment that measures the degree of hydrophobicity of a sample. And then I will move on to test the other geometries from scratch. And ultimately, the best laboratory performances will be evaluated in the injection molding at our industrial partner. And as I mentioned before, the most relevant characteristics that I expect from the molding process is a complete polymer replica with the hierarchical structures, guaranteeing that the plastic containers will be super hydrophobic. Now I'm going to show you two quick videos from my recent results from the goniometry analysis, comparing a flat and a textured polymer. And in the goniometry analysis, a syringe puts a droplet of water on top of the surface and analyzes the contact area between the droplet and the material. And now you can clearly see how a textured polymer enhances the hydrophobicity of a surface. For the flat surface, the contact angle measured was 80 degrees. And for the textured polymer, 138 degrees. And this was just the first test, without the optimized conditions yet. So I expect to have even higher degrees of hydrophobicity after thermodynamic optimization. And in the end, I expect that from my project results, super hydrophobic food plastic containers that store ketchup, mayonnaise, yogurt, cream cheese, ice cream, and many others will be fabricated by our industrial partner. And as a consequence, tons of food waste will be avoided. More plastics will be recycled, and no extra handling will be needed to empty these containers anymore. Thank you very much.
Thank you, Breno. If you have any questions for Breno about his talk, please don't forget to send them in via Twitter or by email. Our second changemaker of the evening is Claire Gibson, a PhD student in the Department of Civil Engineering, working with Professor Dominique Frigon. Claire is going to tell us about how wastewater treatment facilities have become hotspots for antimicrobial resistance. Claire?
Can you imagine a world where something as small as a scrape on your knee or routine tooth extraction could potentially lead to death? Well, without action, we could enter a post-antibiotic era where this could be the case, and once treatable infections and minor injuries could kill. Now, obviously none of us want this to happen, so a series of measures have been put in place to try and avoid this. Current efforts to try and monitor and control the spread of antibiotic resistance often focus on areas with high antibiotic use, such as hospitals and agriculture. We've all become more and more aware over the years that we should only use antibiotics when absolutely necessary. There's also been a push to switch to responsibly sourced meats, which have been produced without the excessive use of antibiotics. But despite all of these measures, one key area that's been neglected are wastewater treatment plants, which have emerged as hotspots for antibiotic resistance and gateways to the environmental spread. Now, wastewater treatment plants are complex systems. They've been shown to contain both high concentrations of antibiotic-resistant bacteria and antibiotic resistance genes, the small pieces of DNA which make a bacteria resistant. When we have bacteria within very close contact of each other, there's also the potential for the transfer of antibiotic resistance genes from a resistant to a susceptible strain, resulting in new antibiotic resistant bacteria, which are well adapted to survive within the environment. To add to this, we also have antibiotic residuals within our incoming wastewater, which introduce a selective pressure, giving resistant bacteria an advantage over those that are susceptible to the antibiotic. But despite all of this, wastewater treatment plants are not designed for the removal of antibiotic resistant bacteria or genes, and so they're released into the environment, contributing to the spread of antibiotic resistance. Now, I know I've just given you a lot of information on one slide, so let's have a quick summary. Wastewater treatment plants contain high concentrations of antibiotic-resistant bacteria and genes, and these genes can transfer from resistant to susceptible bacteria, resulting in new strains of antibiotic-resistant bacteria. We also have residual concentrations of antibiotics, introducing a selective pressure in the system. But despite all of this, wastewater treatment plants do not treat antibiotic resistance, and so these genes and bacteria are released into the environment. So by now, I think it's fairly clear that we need new strategies to control the release of antibiotic resistance from wastewater treatment plants. But this is easier said than done, because between full-scale wastewater treatment plants, there are a number of different variables, whether it be the bacterial community, antibiotic use within an area, or temperature, which makes it very difficult to pinpoint exactly what is affecting the level of antibiotic resistance and to develop appropriate strategies to control this. So my research works on breaking down this process to look at the impact of specific variables. So during this presentation, I'm going to be talking about the role of influent immigration. Now, to understand this term, we need to take a quick step back to look at the biological treatment process. So the biological wastewater treatment process, or the activated sludge process in this case, relies on the activity of microorganisms to break down the contaminants within our incoming wastewater. So upon entry into the wastewater treatment plant, our incoming wastewater is combined with an activated sludge. Now, this activated sludge contains a rich and diverse bacterial community, which is specialized for the degradation of wastewater contaminants. So this mixture of our incoming wastewater and our activated sludge, also known as mixed liquor, then enters an aeration tank, where oxygen is provided for the metabolism of our bacteria and the degradation of the contaminants. The mixed liquor then enters a settling tank, whereby gravity settling, the solid and liquid fraction are separated out, with the solids either recycled within the system or treated and disposed of, and our clean effluent wastewater discharged into the environment. So coming back to this term, influent immigration. So when I talk about influent immigration, we're referring to this interface here between the incoming wastewater and the wastewater treatment plant, looking specifically at how the bacteria within the incoming wastewater affect the bacteria within the wastewater treatment plant. Now, for many years, engineers and modelers have considered the impact of immigration to be negligible. They've suggested that because the bacteria within our incoming wastewater are in relatively low abundance compared to this rich and diverse community within the wastewater treatment plant, that they have little effect. They've also suggested that these bacteria are not well adapted to grow within the wastewater treatment plant, and so that they'll just die out. But more recently, studies have suggested that influent immigration may be important in the maintenance of certain functional groups. So my research aims to address this question once and for all. Does immigration have an impact on the bacterial community within wastewater treatment plants? If it does, how significant is this impact? Do these bacteria even matter? And how does this impact antibiotic resistance? So I'm going to begin by focusing on these first two questions. To do this, I took a bottom-up approach, building up many wastewater treatment plants in the lab, which allowed me to look at the impact of immigration with appropriate reproducibility and controls. All of my reactors were fed with a synthetic wastewater, which allowed me to keep the composition stable throughout time. Then in my experimental group, I supplemented this synthetic wastewater with influent solids taken from a full-scale wastewater treatment plant. So this is my with immigration group. I then had 2 sets of controls. In my first control, which was with no immigration, the reactors were fed with synthetic wastewater only throughout the duration of the experiment. I then had a second control, which was a sterile control, which consisted of synthetic wastewater supplemented with sterilized influent solids. Now, the reason for this is because we wanted to see whether any impact we saw with immigration was because we were adding an additional food source or whether the bacteria were actually actively grown within our system. So all of my reactors were operated in triplicate, as well as with 3 different wastewater treatment plant communities, and then used DNA sequencing to analyze the bacterial communities. So now let's move on to the more interesting part, the results. So here we have a principal coordinate analysis, which is basically a way of visualizing the similarity or dissimilarity between bacterial communities as a whole. So on this graph, each point represents a different wastewater treatment plant reactor, with points that are closer together indicating that they are more similar, and points that are further apart indicating that they're more dissimilar or different. So on the left in black, we see the starting position, which is where all of our reactors were at the beginning of the experiment. We see that in our no immigration group, throughout the duration of the experiment, there was very little change in the reactor community. But as soon as we add in influent solids, even when sterilized, there was a slight change in the bacterial community, indicating that the influent solids either provide an additional food source, or this could be the effect of residual DNA remaining after sterilization. But by far the largest effect we saw was in our group with active immigration. We saw this shift in the bacterial community from left to right, confirming that influent immigration, so the bacteria community within our incoming wastewater, does in fact have an impact on this rich and diverse community within our wastewater treatment plant. So coming back to our initial question, we now know that immigration does have an impact on the bacterial community, but we actually found up to 18.8% of the bacterial community was contributed through immigration. And of these immigrating bacteria, we identified some which have been previously shown to cause operational problems within wastewater treatment plant, as well as others previously associated with antibiotic resistance, which brings us nicely onto our final question. How does immigration impact antibiotic resistance? So to investigate this, I used 2 PCR-based approaches. So PCR stands for the polymerase chain reaction. You might have heard of it more and more over the last years. It's currently being used for the screening of COVID-19, but here we're using it for the detection of antibiotic resistance genes. So PCR is an approach that's used to make thousands of copies of a DNA fragment of interest. So in this case, an antibiotic resistance gene, which increases the concentration to a level that can then be detected. So to do this, we use specifically designed primers, which allow us to focus in on a specific piece of DNA. So in a typical PCR reaction, we'd use 1 set of primers to target 1 antibiotic resistance gene. In the first method that I'm using, we're developing a technique in collaboration with Swift Biosciences, which will hopefully allow us to use around 500 different primer pairs in one single reaction to potentially target around 400 antibiotic resistance genes. We can then use DNA sequencing to identify which antibiotic resistance genes were amplified and therefore present within our samples. Now, the second PCR-based approach I'm using is droplet digital PCR. So typically our PCR reaction would occur in one single tube as shown on the left there. But using droplet digital PCR, we separate our reaction into thousands of tiny little droplets. And in each of these droplets, a PCR reaction occurs. We then use a fluorescence-based approach to identify positive and negative droplets, which gives us a quantitative assessment of the antibiotic resistance gene. Now, I know I just gave you a lot of information on one slide, but all you really need to take from this is that I'm using 2 techniques to analyze the antibiotic resistance genes. One that allows me to detect a large number in one reaction, and another to quantify those of interest. So now let's take a look at some of our results. So from targeted amplicon sequencing, we found that with immigration was a 5 times increase in the number of antibiotic resistance genes present within our system. And this included antibiotic resistance genes to many common types of antibiotics, such as beta-lactams, fluoroquinolone, and macrolide antibiotics. And if you're not necessarily familiar with these classes themselves, they're commonly used in the treatment of infections such as pneumonia, UTIs, and respiratory infections. So they're very clinically important. Now, based on these results, I chose to focus on two groups for further analysis using droplet digital PCR. The first were the beta-lactam antibiotics, which are one of the most commonly used classes of antibiotics worldwide. They're also considered to be last resort when all other treatments have failed. The second group I focused on were fluoroquinolone antibiotic resistance genes, with the fluoroquinolones being commonly used in both human and veterinary medicine. So now let's take a look at how immigration affected the concentration of these resistance genes. Beginning with our beta-lactam resistance, we found that in the incoming wastewater, all of the genes appeared within similar concentration. This also seemed to be the case in our reactors that received our immigrating bacteria, with all of the genes in relatively similar concentration again. However, in our control reactors, the abundance of the antibiotic resistance genes was more variable, suggesting that immigration may play an important role in shaping the antibiotic resistance gene abundance patterns within our reactors. Of particular interest was the BLAR-TEM antibiotic resistance gene, which showed a significant increase in concentration with immigration. We also saw similar patterns in our fluoroquinolone antibiotic resistance genes, with the antibiotic resistance gene abundance patterns similar between our incoming bacteria and our group with immigration, whereas we observe more variability in our control groups, suggesting again that immigration may play an important role in shaping antibiotic resistance gene abundance patterns. Again, we saw a significant increase in two of the antibiotic resistance genes quantified, both the QNRB and QNRS antibiotic resistance gene, confirming that not only does immigration cause an increase in the diversity of antibiotic resistance genes, but it also caused a significant increase in the concentration of half of the antibiotic resistance genes tested. So by combining detailed reactor experiments and multiple techniques for antibiotic resistance gene analysis, we can conclude that immigration does have an impact on the bacterial community within wastewater treatment plants, with up to 18.8% of the bacterial community contributed through immigration. Among these bacteria, we identified some which have been shown to cause operational problems, as well as others previously associated with antibiotic resistance. And by analyzing antibiotic resistance genes within our system, we found that there was both an increase in diversity and concentration of antibiotic resistance genes with immigration. So based on these results, my next step is to look at factors affecting the level of immigration, with a focus on the impact of solid retention time, that is how long the activated sludge is recycled within the system, with the ultimate goal of being able to optimize treatment plant design to minimize antibiotic resistance. And with that, I'd like to thank everyone who's been involved in this project, especially my supervisor, Professor Dominic Frigon, and all of those involved in panel development and reactor operation. Thank you.
Thank you, Claire. If you have questions for Claire about her talk, please don't forget to submit them for our Q&A taking place at the end of the presentations. Our third change maker of the evening is Christopher Ramos, a PhD student in the Department of Electrical and Computer Engineering, working under the supervision of Professor Geza Yost. Chris is going to explain the role that novel switch-based power converters can play in helping us massively scale up green energy plants in order to minimize our dependence on fossil fuels. Christopher?
Our electric power grids have been evolving to accommodate more and more renewable energy sources. Based on worldwide statistics, either solar or wind energy technology is now the cheapest option for new generation in many countries around the world. Just recently, the 2.2 gigawatt solar farm in China and the 1.2 gigawatts wind farm in UK has been completed. These generation plants are categorized among the large-scale renewable energy systems that fuel the tremendous growth in solar and wind energy technology over the years. The good news is, by year 2018, solar and wind energy generation had almost reached 2 million gigawatt hours. But the not so good news is, this is just around 7% of the worldwide energy mix. See, solar and wind is but a tiny fraction compared to coal, which still holds the largest share, amounting to around 38% of the worldwide electricity generation. And if we are to entirely replace coal with solar or wind, then we would be needing around 500 2.2 gigawatt solar farm or 950 1.2 gigawatts wind farm. For both these renewable sources, the only way to connect to the electric grid is via the so-called power electronic converters. But if these sources are located far away from the grid, then we need to transmit harvested power at much higher voltages to minimize the power losses. So, the standard industry practice is to utilize conventional power electronic converters together with line frequency transformers to transmit at higher voltages. However, for this, you need to increase the transformer volume and hence the costs to achieve higher efficiency and longer lifetime. This is true for most but not all transformers. But recently, silicon carbide switch or SiC switch, which is a key part of the converter system, has achieved a major milestone. It can now be utilized at much higher voltages and much faster switching speeds. And because of this breakthrough, my research started to come alive. My goal is to exploit these enhanced features to come up with power electronic converters that can directly perform higher voltage conversion and at the same time reduce the transformer volume and switch count. Now, the transformer is integrated within the converter structure, and here, the black arrow shows the switch locations. Before we go deeper into the details, I need to explain first some electrical concepts to help you understand my research better. Step-up voltage conversion through power electronic interfaces can be achieved either by using capacitive or magnetic elements or both. Capacitive elements are simply called capacitors, while magnetic elements can be transformers or inductors. This is an example of a capacitor. Capacitors can be charged and stacked in series to increase the output voltage. This is an example of a transformer. For transformers, the output voltage can be increased by increasing the number of secondary windings. And this is an example of an inductor. The inductor can be charged through the input supply, and when it discharges energy to the output, it naturally reverses its polarity to provide additional voltage. Here, we can already see how the switches are used to implement the proper sequence of operation needed to step up the voltage. In fact, if you can switch faster, then you can transfer the same amount of energy to the output using smaller inductors. This also applies to transformers and capacitors, such that increasing the switching speed can significantly reduce their volume. So, if we are to get rid of the line frequency transformers and rely only on power electronic converters, then we need to be able to determine if their magnetic or capacitive components can provide sufficient voltage step-up. To do this, we need to study each group in isolation, meaning in one group, only the magnetic elements can increase the voltage, and in another group, only the capacitive elements can increase the voltage. Luckily for all of us, I only need to briefly go through the steps we took, and essentially this involved design, analysis, implementation, and testing. The end product is a converter that mainly depends on transformers, and another converter that mainly depends on capacitors. Let me take you straight to the preliminary results. For a 40 volts input voltage, this graph shows how much a transformer-based converter and a capacitor-based converter can boost the output voltage by increasing the duty cycle. By the way, duty cycle is defined as the ratio of the switch on time to the total switching period. So we tried increasing the duty cycle, and we observed that the 400 volts target output voltage is achieved earlier by the transformer-based converter, implying that it has greater voltage boosting performance than the capacitor-based converter. In terms of efficiency, there is not much difference between the two converters, especially if you go at higher output power. So far, these converter experiments are only from 40 volts to 400 volts. In other words, the output voltage is just 10 times the input voltage. And the output power is only up to 500 watts. But looking back, the line frequency transformers can convert 690 volts to 15,000 volts, which corresponds to a gain of more than 20 times. And in addition, the power level we are dealing with here can be hundreds of kilowatts to several megawatts or more. This brings us to the second question. How can the previous converters be improved to cover higher voltage and higher power operation? Examining the data again, it is unlikely that the previous converters can deliver much further, as here we can see that the efficiency already goes down if the output power is further increased. And earlier, we have learned that the 400 volts output voltage can be achieved by increasing the duty cycle, right? But if I attempt to go beyond 400 volts using the same technique, then the solution will eventually be ineffective, as on the right graph, we can see that the efficiency also goes down if the duty cycle is increased much further. So, how can the previous converters be improved to cover higher voltage and higher power operation? A modular approach is needed. In modular approach, you basically use a converter that can easily be combined in series and in parallel. You do series combination to increase the total output voltage. So the standard switches can only operate up to 6,500 volts, but the newer silicon carbide switches can operate up to 15,000 volts, which means you can use fewer 6 switches for the converter to satisfy the higher voltage requirement of the grid. In addition, you do parallel combination to satisfy the higher power requirement by increasing the total output current. To recap, in modular approach, the higher voltage requirement is satisfied by doing series combination, and the higher power requirement can be addressed by using parallel combination. So we combined our knowledge on how the magnetic and capacitive elements step up the voltage with the modular approach, and finally, the generalized structure of the converter that has been conceptualized is shown in this block diagram. Here, stage 1 is where you combine the units in parallel to address the high currents at the input side. Stage 2 is the transformer stage. So aside from having the option to increase the voltage by increasing the number of secondary windings, this stage isolates the input side from the output side, thus increasing safety. Stage 3 is where you combine the capacitors in series to handle the higher voltages at the output side. And finally, stage 4 is the inverter stage, which converts the DC signal to the AC power signal compatible with the grid. So using the proposed converter framework, we then designed converters that can take an input voltage of 3.3 kilovolts DC and produce 40 kilovolts at the DC bus, which will then be converted to 25 kilovolts three-phase AC at the grid side. The output power must be 5 megawatts at greater than 95% efficiency. From the generalized structure of my proposed converters, 2 unique configurations were generated. So more details about the circuit will be out soon, but as of now, I can only tell you that the 2 configurations contain 172 switches and 12 capacitors. Config 1 uses 6 transformers, while config 2 uses only 1 transformer. Let's now go to the key results. From the simulation at 5 megawatts output power, it can be seen that the 40 kilovolts DC bus voltage can instantly be attained at 1 kilohertz operation for config 1 using 6 transformers. Config 2 shows a much slower response and is unable to attain the 40 kilovolts target if it's just switched at 1 kilohertz. But because of the newer silicon carbide switches, its response becomes comparable to config 1 by increasing the switching frequency to 40 kilohertz using only 1 transformer. And if this high switching frequency feature is extended all the way to the inverter stage, then increasing the switching frequency from 1 kilohertz to 40 kilohertz can significantly reduce the current distortion without using any additional components. Compared to the conventional solution, simulation results also show that the proposed solution is more efficient for both config 1 and 2. In summary, the research is expected to provide a better alternative to conventional converters that utilize bulky line transformers. In particular, the proposed solution is expected to deliver in terms of efficiency, compactness, and compatibility with diverse forms of solar and wind energy sources. Okay, now that you know my research, what's in it for us? It is believed that electric vehicles will be the main mode of transportation in the future. But their low to zero carbon emissions will not make any sense if their electricity source is still being supplied by greenhouse gas emitting plants. But imagine if we can replace all the coal plants with solar and wind energy sources, then our proposed solution can replace the line transformers and deliver clean power all the way to the cities to charge as many as 110 billion electric cars. The only downside right now is the cost of the newer silicon carbide switches, which is expected to go down fast based on trends in semiconductor market. Nevertheless, we are pursuing this exciting research because we hope that the technology can immediately be deployed as soon as the next generation 6 switches become economically feasible for wide-scale use. And as soon as it does, we'll be ready. Thank you.
Thank you, Christopher. I'd now like to open up the floor for any questions for Breno, Claire, and Christopher. We have someone monitoring both our email and Twitter accounts, and we'll try to get to all of the questions that come in. So for the first question tonight, I guess we'll start with a question for Breno. Your example of the ketchup bottle, this is a question from Professor Kopachinski. In the ketchup bottle example, does ketchup have the same properties as water? And would ketchup also be super hydrophobic?
Yes, very good question. So the main idea is to test first the super hydrophobicity. And water is the main liquid that we use to test it, to test this super hydrophobic, because it's easy to test than the other liquids. And the idea is to later on the project to test different liquids with different surface tension values, which means that we're going to test if the structures are also super omniphobic as well, which means that they can also repel not only water, but liquids with lower surface tension, which means they're more dense. So consequently, they will also repel ketchup and any other food like that. And that's the main goal of the project.
Yeah, there's a related question, Breno, which I think comes up to this, which is regarding how oil or fat residues will behave on the modified plastic surfaces. So are these surfaces also lipophobic or fat phobic?
Yes, that's what we are going to test, but very likely they will be, because after the computational thermodynamic optimization, we are going to achieve really high values of superhydrophobicity, and that kind of guides us to a high super omniphobicity. But of course, we are going to test these different surface liquids and surface tension liquids, and to really prove that it also can repel this kind of oily materials or oily liquids. Sorry, yeah.
Great, that's very interesting. Thank you. A question for Claire. You mentioned that there were operational issues related to this bacterial immigration, and what were the issues? How does this, is it something to do with turbidity? And so it's someone who obviously has some knowledge of wastewater treatment plants from the phrasing of the question.
So in this experiment, we didn't specifically focus on operational problems and how they were occurring in our reactors. But when we did bacterial community sequencing, we identified some bacteria such as Thora, which have been shown to cause issues like bulking and foaming, and filamentous bacteria also within our system. So although we didn't quantify the impact that these bacteria may have had, potentially they could cause issues within wastewater treatment plants.
Okay, great, thank you. And maybe a follow-up question, Claire, if you look at the level of antibiotic resistance that we have now in these treatment plants, I mean, how far do we have to go till it's optimal, or when do we know that we've reduced it enough?
Mm-hmm. That's quite a difficult question to answer, because it's all depends on risk, and at the moment, it kind of depends on how much people are likely to be exposed to these genes and things like that. Ideally, there should be non-released into the system, because these genes are capable of transferring into bacteria which are well adapted to survive within the environment and will stick around. So in an ideal world, we would have zero, but this isn't always really doable. So as low as possible, but definitely lower than what we have at the moment.
And I guess also we want to understand how this process happens so that we can, design these systems to at least take us towards that direction, right?
Exactly. We kind of need to understand the fundamental mechanisms before we start trying to tackle the issue of coming up with strategies to deal with it.
Great, thank you. Very interesting. Okay, question for Christopher. Where do you see, what's the scale of the opportunity here for these novel switches? I mean, how, could we implement these in existing facilities? Would that have an improvement? And how do you see this, the demand for such things growing in the future?
Right now, still, the conventional power converters are largely used, and they pair up with line frequency transformers. So this research looks into actually not probably like 5 years, 10 years from now. But yeah, it still depends on many factors. But there has been increasing interest in this line of research, and then many research, more and more research institutions are now researching about the medium voltage grid interfaces that utilizes silicon carbide switches, their enhanced features. So right now, It's not yet that commercially available, but hopefully in the future they will be more available.
So a follow-up question on this coming from the audience from Michael Johnson asks, how costly might it be to change that transmission infrastructure to incorporate the new switches? Are the switches easy to swap into existing infrastructure, or do we need to change the entire system to incorporate them?
Yep. In my opinion, there shouldn't be much difference because the research aims to provide an alternative and hopefully a better alternative. So the way how the line frequency transformers performs its function, the proposed solution will try to like imitate that and give an additional value in terms of making the grid interface more compact and hopefully making it more efficient.
More efficient and more reliable? Is that also, do you believe it?
Yes, but still it depends on a lot of factors.
So that takes the development to further to understand what that reliability and those other impacts are. That's great. Thank you. Okay, maybe we'll come back to some questions for Breno. Question is about these nano features that you etch onto your injection molds. How robust are those, and what impact might that have on, say, the manufacturing cost over time for these types of containers?
Yes, they are going to definitely be very well robust, but because we are actually testing this in two different types of plastics. One is high density polyethylene and the other is polypropylene, and these are really robust plastics. So if we are able to imprint this nanostructures on the plastics, we are sure that they're gonna last longer. And what was the other question? Sorry.
Well, I think the question is not just on the plastics themselves, but on when you've micro machined these molds, these metal molds, okay, does that decrease the life, or will those features wear in time as you're molding container after container?
Yeah, that is actually not a problem. They will really last like for hundreds or thousands of cycles in the injection molding, but the main problem there is that we may have some incrustation of plastics on these nanostructures that can actually avoid the replication of them in the late cycle. So we are actually going to test this. We're going to test multiple cycles and see what's the limitation of the mold and when we actually need to clean these molds before not to start another cycle.
But it should be, so it's more a cleaning and management of those molds rather than having to remanufacture them after.
Exactly, yeah. The mold itself is going to be really, really good. It's going to last really long.
Great. Thank you for that. A question for Claire. Because this antimicrobial resistance is a real challenging problem for society, and we haven't really seen any technological breakthroughs for new antibiotics in decades, how concerned should public health officials be after seeing the implications of your research?
I mean, I think we're at a stage where things can be done. It's just if it's left any longer, potentially in 50 years' time, that this may be a real significant problem. As you said, there's very few new antibiotics in the pipeline nowadays. So ideally, what we want to do is preserve the antibiotics which are actually working for cases where nothing else works, and try and look at all different strategies to control the spread of resistance, because it does spread very rapidly worldwide. It's been shown that upon introduction of an antibiotic, you can see resistance within the coming 1, 2, 3 years, as quick as that. So I think it's a matter of keeping on top of it and doing everything we can to control the spread from different environments, with wastewater treatment plants being one of these key environments. But I think things can be done. It's just action needs to be taken sooner rather than later.
Like so many of the problems that we talk about
Yeah.
in Sedtalks and in TISA generally, is that, you know, we know these problems and we know that there are solutions, but we need to take action on them, right? And that's always that seems to be the most challenging part for society. That's great. I'm trying to look here and scan through these questions. Maybe another question for Breno. Do you have any feeling for what the how the impact of your research and this new technology might reduce carbon, reduce food, container waste, and thereby like carbon emissions? Do you have a sense of the scale of the challenge and how your technology would address that key challenge?
Yeah, we actually don't have that number, and it's really hard to calculate since we are talking about a specific type of plastic that is produced by injection molding. So as I said in the presentation, mostly 25% of the plastics get rejected in the recycling plants because they have food waste in it. So we'll try to kind of minimize this number as much as we can, but actually I cannot predict this in advance right now. But there are some studies that we can actually try to calculate this, but probably it will be done in a later stage of the project.
And another question just came in as you were answering, which asks, are there any risks of these microstructures breaking off of the walls of the container and entering the food supply?
Well, that's a very good question. As I said, these plastics are pretty robust, both plastics that we are going to test. One is also called high density polyethylene and the other is polypropylene. Those are really robust plastics. So it's very unlikely that this will happen. But of course, we're going to at some point test this if they're going to break, if there's going to be any kind of mixture with food, which is undesirable as well.
Because we hear a lot about these microplastics as a key concern now in this area, right?
Exactly.
And then another question came in just as you were answering that one about the aging of these surfaces when exposed to air, sun, time. Are these micro and nanostructures stable? I guess you probably don't have an answer to that, but maybe you can comment on what you think, how those factors might influence.
Yeah, so I'll probably say that it's not going to change much because, as I said, these plastics are pretty robust, and if they're exposed to sun and other different conditions, yeah, I don't really have an answer for that. We should be able to test this somehow, but I expect that it's not going to change that much.
Great. Yeah, well, I think that's an interesting long-term question, and I guess you know, the first step is to see if you can make it work, and then you have to see what are the possible negative impacts that could come, and then address those as we go forward.
Exactly.
Great. Well, I don't see any other questions coming in, so I think with that we'll close the session. At this point, I'd like to thank all three of you as the ChangeMakers for your presentations. I hope that everyone that's joined us tonight in the audience has learned something new, and all of us wish you the best as you complete your projects. I'd also like to thank WSP for their support of Sedtalks and Mr. Eric Passell for his time tonight. On behalf of the ChangeMakers, I'd really like to thank their supervisors for supporting you as you undertook this commitment. I know it's a big commitment, and it takes you away from the lab, but I think you know, in the end, it's a great process for your personal development. I'd also like to extend a special thanks to the Fall Selection Committee, our alumni ChangeMakers, our faculty and industry partners, and all of those who've given their time and feedback to the students as they develop their talks over the past months. There's a lot of actions that happen behind the scenes to make Sedtalks a reality, and I'd like to thank them. Specifically, I'd like to thank the skill set staff, teaching and learning services here at McGill. Specifically, I need to acknowledge the important efforts of Dr. Andrew Churchill in working with our students throughout the program from the fall and through the 3-minute thesis competition and all the way through this winter semester. Andrew's made a big difference on this program with his involvement. I'd also like to thank the McGill Media Services team for their behind-the-scenes expertise. Certainly this year more than ever. It's been important to have that, and they're getting very good at doing video recording over Zoom. I'd also like to thank the TISA team for their efforts in helping to organize and coordinate tonight's event. We certainly couldn't do it without their important efforts. Finally, I'd just like to say that our ChangeMakers have presented what's really a small snapshot of sustainability research at McGill. I hope that they can inspire other graduate students from different disciplines across our faculty to take part in this program in the future. And on behalf of TIEZ, I'd like to thank each and every one of you for being part of our 2021 Sedtalks event. Please stay safe and healthy. And I really hope that next year we'll be live once again. And I look forward to meeting each of you then, and maybe eating some canapes and drinking some drinks as well. Thank you and good night.